buoyant force due to the balloon, and I've got a buoyant force due to the shipping container. Two upward forces, and then they say ignore the weight of the balloon. It's a very thin balloon, not very heavy. What's keeping this thing on the ocean floor initially? Its weight, right? Mass, shipping container times G. So notice we're going back to free body diagrams. We're identifying the forces. Now, and from that we write our equation. So, force, buoyant balloon, plus force, buoyant shipping container, minus mass shipping container times G. And in the problem statement they say, oh, it just barely lifts off the bottom, but it's not actually accelerating yet. So we assume it's in equilibrium, okay? That's how I can say that. If it was accelerating, I would have MA over here and we can figure out the acceleration. But let's focus here. How do I get the buoyant force on the balloon? How do I get any buoyant force? I'm gonna call on somebody back there. David! He got serious all of a sudden. How do I get the buoyant force on the balloon? Just in general. Upper left corner. Upper left corner. What is it?
Rho VG.
Rho of what?
Fluid. Volume.
Which fluid?
Salt water.
Salt water times
Volume.
of what? Of what?
The
Balloon. Did I spell balloon right? 2 L's and 2 N's?
1 L, 2 L.
Is it 1 L?
There's 2 L's.
Okay. Not asking anyone anymore. All right. Hey, listen, this is important because you guys will screw this up. Well, that's why I'm going over these slowly, because it's sometimes hard to get your head around it. It's the fluid displaced that provides the buoyant force. It's the volume of the object that pushes aside that fluid. And then G is just figuring out the weight. All right, now, the buoyant force of the shipping container, it's also pushing aside salt water. Do you agree? And the shipping container has a volume associated with it. Volume, shipping container, G, minus mass, shipping container, G, equal 0. This is the basic starting point. Please write this part out and make sure you identify what you're finding the volume of and what fluid's being pushed aside, or you'll mess it up.
That's extremely heavy.
I don't want you to. All right, so what's the volume of a balloon? This is 1025, right? This is 4/3 pi times 1.5 cubed. That's the volume of a sphere. And we'll do the numbers in a bit. And of course, this is, oh, we can actually, you see we can cancel the G everywhere, guys?
Oh, we can. Is that because you're not trying to find what you're trying to find mass?
Right. If I were trying to find weight, I'd have to keep G. I can just leave it in there. No, let's take it up. All right, plus 1025. And what's the volume of the shipping container? It's length times width times height. Yes? What did we come up with for that, somebody?
38.06.
What is it?
38.06.
30.06 minus the mass of the shipping container. I think that's all there, correct? Do I have everything filled in? Any questions about this volume? This is the spherical balloon. This is the box, shipping container. Now, it's plug and chug, right? Calculate, you should get, what'd you guys get?
53505.
53505. I agree. Kilograms. Within some rounding error, you might have something slightly different. What's that? Point whatever.
53
Are there questions about this problem? Notice I identified the forces first. Don't forget, if something's in a fluid, there's a buoyant force on it. Okay, now I want to talk about icebergs, because it's fun. So, you probably remember back in kindergarten or wherever that somebody gave you some obscure number that said only so much of an iceberg is visible. You guys remember what that number is? 10%. Thank you, Jake. What's that? So, you might have heard this piece of information, but now I'm going to show you why it's true. So, only 10% of an iceberg is visible above water. That implies the rest of it, the other 90%, is below water. What's that? I have an iceberg. It looks like that emoji. Talking about icebergs, okay? So icebergs are made of ice. Very good. Well done. What's the row of ice?
No idea.
917 kilograms per meter cubed. And what's the row of salt water?
10.5.
25 kilograms per meter cubed. You guys ready? Now, looking at this as an object, what are the forces acting on the iceberg? Weight down and buoyant force up, correct?
Yes.
Okay, so force, buoyant, down, and iceberg, and iceberg times G. Do you agree? Okay, icebergs are floating. It's floating. So what do I know about these forces? They're balanced, okay? All right, so up minus down. Equals 0. All right, now make me proud. You guys ready? Gotta make me proud. What is the buoyant force on the iceberg? Row of what? Row of the liquid we push aside. Now let's be very careful here. I multiply by the volume of the object that is submerged, pushing aside the water. Is this part of the iceberg here pushing aside any liquid? No, it's only the part below the surface that is pushing aside the water. Do you understand that fact? Okay, so it's times the volume of the iceberg below the surface. Does that seem reasonable? The buoyant force only arises because some volume has pushed aside some liquid. Times G, yes? Minus.
The mass of the iceberg.
How do I get the mass of the iceberg? Put it on a scale. Yes. So I take density of ice times the volume of the iceberg. That's the entire iceberg, right? If I want to get its weight, I take density times the entire volume times G equals 0.
Would you be able to cancel out G in this situation?
Yes. ready? Let's check it out. So now I'm going to say rho saltwater volume of iceberg below the surface equals rho of ice total volume of iceberg, all of it. So if I take a ratio, the volume of the iceberg below divided by the total volume of the iceberg. So I divided here, I'm going to take this and divide by that. What is the density of ice divided by the density of salt water?
Very small number.
Not a small number.
1.1.
Not one. This divided by that.
0.89.
0.89.
It was a small number.
That's not a small number, it's a percentage,
Um,
right? This is telling me, think about what this is telling you. The volume of the iceberg below the surface divided by its total volume is 90%, which implies how much is above the surface?
10%.
10%. QED. Thus I have proven it. This is why 10% of an iceberg is visible, while 90% lurks below the surface, Titanic. What's that? 10% is above the surface. By the way, in general, if you have two things of differing densities like this, like ice and whatever the differing densities are, you can get the percentage of the volume of that object below the liquid and above the liquid using the same ratio. Just make sure you use the right densities. It works for any object. Notice I didn't even calculate the volume. I didn't need to know the volume of the iceberg to make this work. Right? It's all about the ratio of these densities that determines what happens. That's too cool for school. Come on, guys. Give me something.
Oh, yeah.
Woo!
10%.
10%.
Go home and show your moms, and they'll be like, oh, that's well worth the tuition. I'll go, that piece of trivia right there.